Today we're going to dig a little bit deeper into what the mean really is. So we're going to be looking at the mean of a random variable. And when we talk about the mean, what we're really talking about is the expected value, what we expect to come when we perform an experiment using that random variable. So let's take a look and see how we could do that. Here we have the definition of the expected value or mean of a random variable x. Now a random variable is going to have probability distribution f of x. And let's first consider the case where our random variable is a discrete random variable. We're going to find the expected value or mean by taking the sum over all the possible values that our random variable could take of the product of that value that it takes times the probability of that value happening. So this should feel familiar to taking the mean before. So say we have an experiment. In this, we're going to flip 3 coins and we're going to count how many heads we have. So our possible values for our random variable are 0, 1, 2, and 3. Now say we conduct this experiment, well, let's go with 10 times, and we end up with 0 heads coming up 2 times, 1 head coming up 4 times, 2 heads coming up 3 times, and 3 heads coming up once. Now the way we took the mean before, if we were trying to come up with what was the average number of heads, we would take 0 times 2 plus 1 times 4 plus 2 times 3 plus 3 times 1. And then we would divide by our 10 iterations. Now, our definition of expected value is asking us to do basically that. What it's doing is it's taking the 0 number of heads and it's multiplying by 2 over 10. And then it's adding to that the 1 number of head and multiplying by 4 over 10. And then it's adding to that 2 heads times 3 over 10. And adding to that 3 times 1 over 10. So all it's done is taken and broken this into fractions by pairing the number of observations we have, our denominator, up with each of the parts of our summand, and these two things are actually equal to one another. Now what's different about this and my definition is really simply how much I can apply my definition. So before, I needed some kind of experiment to be conducted. Now, I can do this if I just take a look at what the probabilities are. And so I can do this completely theoretically, and I don't need that experiment to be a driving force. Additionally, before, we only had the mean defined when we were dealing in discrete random variables. Now I can generalize this since I'm thinking about a sum over all the possible values. For a continuous random variable, the equivalent of that sum over all the values is the integral from -infinity to infinity of that product, x, the possible value, times the probability distribution f of x, dx. So let's take a look at an example in the discrete case. So we have a lot containing 7 components that's being sampled by a quality inspector. The lot contains 4 good components and 3 defective components. A sample of 3 is taken by the inspector, and we're supposed to find the expected value of good components in the sample. Well, the first thing that we need is our probability distribution. So if I want to find f of x, I need to think about a denominator of how many possible ways I can choose 3 components. And then if I am choosing x good components, then there's 4 of those that I'm choosing from. And then from the 3 defective components, I'm choosing the remaining ones, so 3 minus x of them. And I know that my x values, I could have no good ones, I could have 1 good one, 2 good ones, or 3 good ones. So those are my 4 x values. So I'm going to plug in my 4 x values and go on and find my 4 f of x values so that we can work with those. So now that I have the values for my probability distribution, I can use my definition and say my expected value of x is going to equal the sum over all the values of x, so 0, 1, 2, and 3, of x, f of x. And this is going to equal, plugging 0 in, I have 0 times f of 0, plus, plugging 1 in, I have 1 times f of 1, plus, plugging 2 in, I have 2 times f of 2, plugging 3 in, I have 3 times f of 3. And then I just substitute in the values I've already found for my probability distribution. So I have 0 times 1/35 plus 1 times 12/35 plus 2 times 18/35 plus 3 times 4/35. And when I do all of my multiplication and addition, I end up with 12/7, which is about 1.7 good components. Now, one quick thing that you should check always when you do these is your expected value should always fall somewhere in the range of values for x. It doesn't have to be exactly one of the x values that it could have. For example, I can't have 1.7 good components. I can have 1 or 2 though. And so 1.7 is a reasonable answer for this. If I had worked all of this out and ended up with something like 5 point something, then there should have been little alarms going off in my head to tell me that something's wrong in my arithmetic, because I can't have that many good components. It's not possible. And the expected value should really be kind of a measure of center. It should be fairly central in your data when it's weighted by the probabilities. Now let's take a look at an example with a continuous random variable. So we're going to have x be the random variable that denotes the life in hours of a certain electronic device. So we're given a probability density function, and we're asked to find the expected life. So the expected life is the expected value of our random variable. And so we can just use our definition, and we know that the expected value of x is going to equal the integral from negative infinity to infinity of x times f of x. So in this case, it'll be x times 20,000 over x cubed dx. So we can see that this is for x is greater than 100. Otherwise, it's 0, so the integral there everywhere else is 0. So we have a minimum value of 100 here. And I have an x in my numerator and an x cubed in my denominator, so I really have the integral from 100 to infinity of 20,000 over x squared dx. Now, taking this integral, I end up with negative 20,000 over x, 100 to infinity. Now, calculus-wise, some people are cringing right now, right? hopefully. But notice if we plug infinity into this, as we move towards infinity, our limit as we go to infinity, the value of this is 0. And so this is going to be 0 minus a negative 20,000 over 100, which equals 200. So our expected value is going to be 200 hours. Sometimes we have random variables that depend on other random variables. So in the case that we have a random variable g of x that depends on a random variable x, we can actually still find an expected value for that dependent random variable. So the expected value for that dependent random variable g of x in the discrete case is going to be the sum over all of the random variable x values of the product of g of x times f of x. And in the continuous case, we're taking the same integral, negative infinity to infinity, of g of x times f of x dx. So we're using the values of the random variable that g of x is depending on to find the expected value of g of x itself. So let's take a look at an example with a continuous random variable x and a density function f of x, where we're asked to find the expected value of some random variable g of x equal to 4x plus 3. So to do this, we can simply find the expected value of g of x, or 4x plus 3, by following our definition. So we'll take the integral from negative infinity to infinity of g of x, 4x plus 3 times x squared over 3, our f of x value, dx. Now, x is restricted to negative 1 to 2, so we're actually integrating from negative 1 up to 2 for this. And when I do this, I can pull the 1/3 out front, so I have 1/3 times the integral from negative 1 to 2 of 4x cubed plus 3x squared dx. So this is 1/3 times x to the 4th plus x cubed, evaluated from negative 1 to 2, which is equal to 1/3 times 16 plus 8 minus negative 1 to the 4th is positive 1, plus negative 1 to the 3rd is negative 1. So this equals 1/3 times 24, which equals 8. So my expected value of my random variable g of x is 8. And our idea of finding an expected value, or a mean, isn't limited to just a single random variable. We can actually work with joint probability distributions, f of x, y, to find the expected value of a random variable that's dependent on two random variables, so g of x, y. So we do this by taking the double sum, summing over x and summing over y, of g of x, y, f of x, y, where we're going through all the possible values of x and all the possible values of y with our sums when x and y are discrete. And we do it with the double integral, integrating over x and y from negative infinity to infinity of that product g of xy times f of xy when x and y are continuous.